any type of compound is represented with a chemical formula. Now, I'm sure you've seen those, like H2O, CO2, NaCl. And you need to make sure you know how to read these. I think they're probably pretty clear. The letters represent the element symbols from the periodic table. The subscripts tell you how many atoms of that element shown are present in the compound. So in this case, we have 2 oxygen. In this case, in the bottom, we have 4 chlorine. Okay, so that's pretty easy, I think. All right, so now we're going to talk a little bit about the 2 different types of formulas. We'll actually be doing calculations on these in the next part, or in the last part of Chapter 3. But the 2 types of chemical formulas are an empirical formula. An empirical formula is just a mathematically simplified form of the real formula, which is called molecular formula. What the heck am I talking about? It's always best to look at an example. If we have a chemical formula called C4H8, that happens to be butane. You don't need to know that at this point. That's what goes in cigarette lighters. But anyway, so C4H8, you ask yourself, can it be simplified? And I just mean mathematically. So you look at the subscripts, and can they be divided by a common factor? Yes, in fact, they can both be divided by 4. And so therefore the empirical formula for butane is CH2. Pretty simple so far, huh? So, for example, if you have a molecular formula B2H6, you can divide both of the subscripts by 2, and the empirical formula would be BH3. You do have some molecular formulas, for example, carbon tetrachloride, which cannot be mathematically simplified, and so in that case, the empirical formula and the molecular formula are identical. So, in some cases, they will be one and the same. All right, so I'm not really going to talk about these, but in your homework problems and on tests, chemists have a variety of ways that they show a compound. Obviously, you can have its name. You might have the empirical formula, so you've got to be careful what type of formula they tell you they're giving. You can have the molecular formula, which is the real formula. It tells you exactly how many atoms of each element are present. Then you might have what we call a structural formula, where for whatever reason we want you to know something about the shape of a compound, or what elements are bonded to what elements. And so that would be a structural formula. So you can see they tell you if they have single or triple bonds. They tell you which atom is attracted to or is bonded to which other atom. Sometimes if they want you to see 3D geometry rather than using just letters and typeface, they will use what we call ball and stick model. You can see more what the shape looks like. And then more recently, some chemists have said, well, the ball and stick model is not very representative. The space filling models are more representative of what atoms really look like in real life. And so these 2, for example, are considered to be equivalent. All right, so just kind of a flow chart for those visual learners to help us look at some of the difference we've talked about here. So I don't know if you remember from Chapter 1, but in Chapter 1 we divided matter. We had matter up at the top here. And we said matter could exist as either a pure substance or a mixture. We'll talk about mixtures more later on too. Oh, I can't get my E in there. There. And so we're not talking about mixtures today, but anyway, so this is the branch of pure substances, and we went on to then say pure substances can either be an element, those are all on the periodic table, or it can be a compound, which involves chemical bonds. Well, today I want you to make sure that you understand that elements don't have to be single individual atoms. Elements don't have to exist as isolated atoms. Some elements actually already exist as a molecule. Okay, some elements in our daily lives, in our world, exist in nature already as a molecule. So I'll talk about which one of those do that, but it is possible to have molecules that are in fact elements. Compounds have to have at least 2 different elements to be called a compound. And so we have the molecular compounds. Remember, those are the ones that have covalent bonds. We call those molecules. And we have ionic compounds, which we called the little isolated group here, we called a formula unit. Okay, so that's just kind of a look at the big picture of what we're talking about, all the different species. All right, so this is something you're actually going to have to memorize. The elements that exist in nature, already chemically bonded, so they're in molecular form. All of them are covalently chemically bonded, and so they are called molecules. There are 7 of them. And some teachers give a little mnemonic memory trick. Hofbrinkel, it's just a meaningless word, but it's easy to remember, and it helps you remember all 7 of the diatomic. They're diatomic obviously because of nature. They all exist as twins. They come out in pairs. You will never see one of these on their own naturally. And then the other 2 elements that exist in molecular form already are phosphorus and sulfur. Kind of weird how they choose to exist. All right, so another way to remember the diatomics are, remember there are 7 diatomics. So this is kind of a cool little trick. So if you start at hydrogen, because it's element 1, okay, then you go over to element 7. Remember there are 7 diatomics. And you draw the number 7, you will get all of the diatomics. So that's kind of cool, huh? And then the other molecular elements are tucked right inside of the number 7. So it's just kind of a visual way to remember. All right, so again, a molecular compound is a compound that has covalent bonds. They involve 2 nonmetals, and blah, blah, blah. There's nothing else I really want to talk about here. All right, so again, a summary of ionic compounds. They involve a metal and a nonmetal, which have been, by donating an electron, have become a cation and an anion. And then the cation and anion are held together by the electrostatic attraction between opposite charges. An ionically bonded compound has what we call formula units. So if you were to go into this 3D array, and if you could pull out one formula unit from that big thing, NaCl, that would be a formula unit. Okay, right here. Molecules already exist as individual compounds. Like water, if you could go in with small enough tweezers, you could pull out an individual H2O molecule. It's only ionic compounds, because of the really strong electrostatic attraction that exists in this 3D array. All right, so one thing that throws some students off, so it's worth mentioning here, is that you have some ionic compounds, like the 3 I've shown here, and you might get confused if you weren't aware of what they were. So the first thing you will learn to do when you're looking at chemical formulas is you will learn to ask yourself, is there a metal in this formula? And in this case, yes. Hopefully you've printed out your periodic table. If not, you should do that. They all have a metal in them, and you'll see the metals are shown first. Sodium, calcium, and potassium are metals. And so you would be right to say, okay, if I see a metal in a formula, that means it's an ionically bonded compound. That's correct, okay? But then you might look further and say, now wait a minute. It's also supposed to be, a metal supposed to be bonded with a nonmetal, but this has 3 nonmetals in it. What's going on? It turns out that when you have more than one anion, well, they make up a single anion, but when the anion has more than one element in it, it is called a polyatomic ion. Okay? So NO3, CO3, and ClO are all polyatomic ions. And the polyatomic ions themselves have covalent bonds, because look at NO3, for example. It has a nitrogen in it and an oxygen in it. Nitrogen and oxygen are both nonmetals, so they have a covalent bond between them. But overall, this compound is still ionic because it has a cation and an anion. I hope that didn't confuse you. All right, I kind of already gave you a summary, but so I think you already know the first dash. The second one is very important to know as we start naming compounds and writing formulas ourselves. Keep in mind that the sum of the charges in an ionic compound must be overall 0. So what does that mean? That means the charge of the cations must equal the charge of the anions. Okay? Must be as much positive charge as there is negative charge, so that overall there's no net charge. Okay, and ionic compounds the formula unit always represents the simplest ratio of elements. So you won't ever see, in an ionic compound, you won't ever see a formula that you can simplify like you can in covalent. Okay? Yeah, you'll always already see the simplest ratio of elements. Alrighty, so just a reminder, I think I went over this in Chapter 2, but just a reminder for you. The metals are to the left of the stair step, and metals typically lose electrons to become cations when they undergo a chemical reaction. And so all of these metals will get positive charges or cations. The reasons that I haven't shown the transition metal charges is because they vary. Sometimes the charge is +1, sometimes +2, +3, or +4. So the transition metals are unique. However, the metals are in what we call the A groups, we call those the representative groups, always have the same charge. And so we can just memorize those, and that helps us a lot when we're learning to write formulas and names. So group 1A, always, when they become cations, always get a charge of +1. Group 2A, when they become cations, has a charge of +2. Group 3A, the ones there are of them, get a charge of +3. 4A, that's the carbon group, does not tend to make ionic bonds. They have an equal, well, we'll go over that later. And then it's kind of a mirror image here. You've worked up in charge, and now we're going to kind of approach it from the other direction. So the nitrogen group, now we're in the nonmetals, and they tend to gain electrons, so they become anions. And so the nitrogen group tends to gain 3 electrons and have a charge of -3. You can see what I mean by mirror image. +3, -3 are right next to each other. The oxygen group, when they become ions, have a charge of -2. And I just don't even want this over here. Okay, and the halogens have a charge of -1 when they become ions. So those you should definitely memorize. Okay, you're going to need those. Alrighty. This is just terminology. This is just to remind me to tell you that when you read something that says main group elements, they're talking about the yellow. They're talking about everything but the transition metals. Okay, just so that you know that. All right, as I said before, the transition metal can have variable charge when they become an ion, and because of that, it is trickier to write formulas for ionic compounds that have transition metals. And so just to give you an idea of what you'll be dealing with those, let's say you have a formula FeSO4 and I ask you to name it. You can't just say iron sulfate. We're going to talk about, I haven't even taught you how to name yet, but that would not be correct because the iron is a transition metal, and in some cases it has a +2 charge as a cation, other cases a +3. And so you have to have the knowledge of what charge the transition metals have because that becomes part of their name. And so I just want you to keep that in mind with transition elements. There are 3 non-transition elements. They're close to the transition metals. They're to the left of the stair step, but they're not smack in the middle, so they're not purely transition metals. But lead, thallium, and tin behave as